We don't typically compute the variance from the expected squared deviation. There's often a more convenient way, which is what I'm going to describe. So more convenient computation of variance. And this is often the way in which we do it. And when you understand a deviation, you first compute the variance and then take the square root. Okay. So let's look at what the variance is. So the variance is equal to the expected value of the deviation squared. Okay, and what's that? That's the expected value of the random variable x minus its mean. So x minus the mean squared. So this is all review of the definition. Okay, and now let's multiply out this square. So this is the expected value of x squared minus 2 mu x plus mu squared. Okay. Now we're going to use this fundamental rule for expectations, which is that the expected value of a sum is the sum of expected values. So this is equal to the expected value of x squared minus the expected value of 2 mu x plus the expected value of mu squared. Okay. And now, again, linearity of expectation, you can pull a constant outside the expected value. So this is the expected value of x squared minus 2 mu times the expected value of x, okay, and then plus the expected value of mu squared, which is just mu is a constant, so it's the mean of the random variable. It's not random, it's just a constant. So this is plus mu squared. Okay. So this is equal to, and now the expected value of x, this is mu. So this is equal to the expected value of x squared minus 2 mu times mu, so minus 2 mu squared plus mu squared. So minus 2 mu squared plus mu squared is just minus mu squared. So this is equal to the expected value of x squared minus mu squared. Okay? And so let's summarize this in a box. So the variance, okay, which is the expected value of the squared deviations, is equal to the expected value of the random variable squared minus its mean squared. And what's that? It's the expected value of the random variable squared minus, what's the mean? It's the expected value. So it's the expected value of x, that's the mean, squared. So notice the difference. Here the square is inside, here the square is outside. So the expected value of x squared minus the square of the expected value of x. So this is a very important formula. Let's box it. This is typically how we compute variances. Okay. And what it means is that we have to compute two expected values. One for the expected value of the random variable, the other for the expected value of the random variable squared. Okay. And then we take the difference of one minus the square of the other. Okay. So let's do an example. Okay. Or examples. We'll do a bunch of examples. So the first one is the sum of two dice. The sum of two dice. Okay, so we know, so this is our random variable x. We know that the expected value of x is equal to 7. The expected value of a single die roll is 3.5. For 2, you get 7. Okay, twice that. Okay, so now, to use this formula for the variance, we have to compute the expected value of x squared. So the expected value of x squared. So you take the squares of the possible values, weight by the probability of that possible value, and add. So this is equal to 1 over 36 times 2 squared plus 2 over 36 times 3 squared plus y2, because that's the possible value 2 for the random variable. And we're computing the square because it's the random variable squared, plus 3 over 36 times 4 squared plus 4 over 36 times 5 squared plus 5 over 36 times 6 squared plus 6 over 36 times 7 squared plus 5 over 36 times 8 squared plus 4 over 36 times 9 squared plus 3 over 36 times 10 squared plus 2 over 36 times 11 squared plus 1 over 36 times 12 squared. So why did I write this whole thing out? Just to show you that there's nothing suspicious going on. There's nothing magical. It's just a brute force calculation of the expected value of x squared. The standard way. Okay. And if you evaluate this whole expression, you are going to get 54 and 5/6. Okay, so that's the expected value of the sum of two dice squared. It's the expected value of that square. Okay, and the expected value of x is 7. So we expect from this formula, which has to be true because we derived it. So the variance is equal to the expected value of x squared, so 54 and 5/6, so 54 and 5/6, minus its expected value squared, minus the mean squared, which is minus 7 squared, minus 7 squared, which is 54 and 5/6, minus 49, which is 5 and 5/6. And we already got this value for the variance by computing the expected squared deviation. It's a good thing they gave the same answer, and we derived that they have to. Okay, so this is another way to compute the expected value, and it tends to be more convenient. Okay, let's do a couple more examples. Okay, so the Bernoulli, or the binary random variable. Okay, remember, the random variable is equal to 1 with probability p, and 0 with probability 1 minus p. So the expected value of x is equal to p. We already computed this. Now what's the expected value of x squared? So you take the squares of the possible values and weight by the probability. So 1 squared is 1 weighted by the probability p. Okay, so this is p times 1 squared, p times 1 squared plus 1 minus p times 0 squared, which is p times 1. 0 gives you 0, so that's p. Interesting. So for the Bernoulli, the expected value of the square and the expected value of the random variable itself are the same, p and p. Okay. Okay. And so what do we get for the variance? The variance is equal to the expected value of the square, p, minus the square of the expected value, minus p squared, which is p times 1 minus p. Okay? So that's a useful formula to sort of have in your pocketbook. The variance of a Bernoulli. It's p times 1 minus p. Okay, what about the uniform random variable? The uniform. And now you'll see why it's much easier to compute this way rather than computing deviations and then taking the average. The uniform on 1 to up to n. Okay, so and remember, if it's uniform on 1 to up to n, then the probabilities are 1 over n up to 1 over n. So all the probabilities are the same. So we computed the expected value some time ago. Okay, so the expected value, so this is x. So the expected value of x, we computed it, is n plus 1 is 1/2 n plus 1. Okay, in the usual way. Now let's compute the expected value of x squared. The expected value of x squared is equal to 1 over n times 1 squared plus 1 over n times 2 squared plus and so on, plus 1 over n times n squared, which is 1 over n times 1 squared plus 2 squared all the way up to n squared, 1 squared plus 2 squared plus all the way up to plus n squared, okay, which is 1 over n times 1/6 n plus 1, 2n plus 1. So that's a common sum. Okay, the sum of the first n squares. The n's cancel, and we get that the expected value of x squared is 1 over 6 n plus 1, 2n plus 1. Okay, and now we can get the variance. Well, the variance is equal to the expected value of x squared minus the square of the expected value. So we get 1 over 6 n plus 1, 2n plus 1 minus the square of the expected value, 1 over 4 n plus 1 squared, which is 1 over 12 n squared minus 1. So now you can do the algebra to fill that in. Okay? I want to mention an important theorem. Okay? And it follows from the fact that, we already said that the variance is always positive because you take deviations, you square them, weight them by positive probabilities, and add. So the variance is positive. Okay, and so what does this mean? This means that, any way you compute the variance has to give you a number that's non-negative. Let's say it's non-negative. It's not necessarily positive, it's non-negative. So this formula that we have for the variance, which is that it's the expected value of the square minus the square of the expected value, says that the expected value of the square minus the square of the expected value has to be bigger than or equal to 0 for any random variable. Well, this means that, the expected value of the square, is always at least as large as the square of the expected value, which is mu squared. Okay, so this is an important fact, okay, that for any random variable, the expected value of the square is always as large at least as large as the square of the expected value, always. Okay, now, let me erase that side and let me talk about linearity of variance. Okay, it's not quite as easy as the linearity of the expected value. So the expected value of a sum is the sum of expected values. Doesn't quite hold always for variance. Okay, and let's see when it does hold, and we'll use that as one application of linearity of variance. We will compute the variance of the binomial. Okay, so let me erase and talk about linearity of variance.